I thought we'd continue on with our discussion. Like I mentioned, I don't have that many more to go, but I have a little extras here that I might also cover that during this period. And tomorrow, you'd like to work two problems. I hope we have time. One on a gas problem where we're going to do a two-layer system. You know, you've just developed the forecast by hand, go through the hand calculator. I've already done it myself. And then there's another one that I did try and prepare for this class, that a single phase, we used a simple exponential decline to try and demonstrate a problem of layered no crossflow reservoir, and where we're going to do some infill drilling and see what type of responses we're going to get from the infill drilling, and then compare it to some figures that have been published where the implication is that these responses and this characteristic that you see, the big responses and what have you, is completely due to areal heterogeneity, whereas in reality each of our layers is going to be exactly homogeneous, equal permeability and thickness everywhere and porosity. And just to show you that you can get that type of response, plus the fact that you go back and read some of these papers, and you're going to get copies of them, you'll find that a lot of the early fields, particularly the carbonates that were developed like in West Texas, and usually people think the carbonates are a lot more discontinuous than sandstones, were drilled and completed basically open hole. The wells were originally stimulated, commingled. In some instances, because everybody assumed that they were homogeneous in the vertical communication, they even stopped, not very deep into the reservoir. And you find those situations, if you have no crossflow, you have a real good potential, and people get surprised. When they deepen a well, they find out that they have got a reservoir beneath that has never been produced before, because of the assumption, everybody's assumption, that everything is in vertical communication, particularly carbonates, and in some instances where you know that they're very highly fractured. What we have here is a schematic of the model study that we did for the Oklahoma Hugoton field. I showed you where it was on the map, about where it was on the field itself, and what we ended up with was a 12-section model where each section is a mile square. And the wells were normally drilled in the center of the section, which you can see. These are the actual physical locations. 4x3, we really weren't sure at this stage how big we could go. Now, after we did it and we realized how much easier it was going to be, because we understood layered no crossflow, we could have probably built a bigger model, but we didn't know if next month or the following month the Oklahoma Corporation Commission was going to call a hearing. So, we picked up something at least that wasn't one well. And we were originally going to build a 3x3, but after we looked at that location and said, wait, there's right to the south, there's a section where a replacement well was drilled. And if we can match that, we're going to demonstrate that we have the ability to predicting what an infill well would do if it was drilled somewhere in a given section. We ended up with 3 layers, the Harrington, the Kreider, Winfield, with a shale barrier in between. We didn't put it in the model, we just had 0 crossflow. Or we input 0 crossflow for the basic history matching case. After we got it matched, then we opened it up to see what the effects would be of crossflow. We did some initial studies. Demonstrate that if we had a 9x9 grid within a section, that we could simulate the 72-hour shut-ins and a 72-hour drawdown. This is going to be our history matching. You're going to match the pressure versus Qm and the official deliverability tests. Again, the pressure versus Qm basically matches the in place, or the gas in place, and the deliverability is going to match the KH and skins on the wells. And at the buff section, we drilled an expendable well that we cored. You got core data, layer pressures while we were at it. We had Helen Farrell, you take a look at the core, and I think we cored one in the shield, at least, down there too. We weren't able to get layer pressures on that one because they were drilling it for a different purpose, and they didn't want the expense, but we did core and get that information. We had Helen Farrell take a look at the core data, and she said this is the least naturally fractured carbonate she's ever seen. So this, what I told you earlier, when you compare the KH from the log or the core data, to try and describe the KH in a crider, it was an order of magnitude less than what we got from pressure transient testing, which was important. Had we described the entire system at T equals 0 strictly by core alone, we would have been off on what we were predicting into the future. We had flow after flow tests. I'll show that next. We had flow after flow tests on each of these wells. We had a policy in the gas department, whenever a well was completed, it was multi-point tested after it was cleaned up. Well was cleaned up. So these are the wells that were in our 12-section study area, and you can see the test dates run all the way from, well, the initial completions really, from 1946 to about as late as 1948. 4 flows per well, or per flow, and some of these flows were 24-hour flow periods. We had a few that were only 3, but they were flow after flow. We hadn't discovered, or Calder hadn't developed the isochronal method of testing, which the only difference there is you shut the well in between each flow to let the shutting pressure build up to get rid of the transient. So these flows, when you run flow after flow, you have a transient effect built in as a result of each of the previous flows. So you can end up with a problem trying to analyze them straight. These were the KHs that we got from the analysis, and you can see they range. There's one sticks out like a sore thumb. You have the Vantine about 1340 millidarcy feet. And look at the skins that we were getting. This is from the test results alone. We'll look at the skins. I think they average at least about -5 on the wells, and they were just acid fracked. And again, the original wells, we stimulated starting from the bottom. We stimulated the wind field. The fact that was normally wet, we did as small a job as we could in hope we didn't acidize in the water. If we did, we just plugged it off and left it. Then we went up into the with a crider, perforated, stimulated. I set a bridge plug. I perforated the Harrington, stimulated. I drilled out the bridge plugs, and then commingled, acidized them all, to clean it up. You blew the wells there for maybe about 3 days to clean up from the acid treatment. You shut them in about a week, and then we ran the flow after flow test. And out of those tests, again, these are the KH and skins. I can tell you now that from the original pressure transient values that we got on these wells, from the original test, not a single value of KH was changed on any well, and all of these skins remained exactly the same as the ones that we calculated. There was a minor adjustment here in skin, like here from -469 to -515, which isn't very much, from -542 to -5, to match the 72-hour deliverability flow tests, okay, the official tests that were run over a period of 45 years. We matched all that data. To show you what a 1945 data looks like, I see a lot of people badmouth or are not even aware of multi-point tests, or say that they're no good. Part of the reason why is a lot of people think that all you do is measure the flowing pressure at the end of a flow period and a rate, and you plot that data, and that's it. Well, in the gas department, what we did was we measured pressures and rates every 15 minutes with a deadweight tester. Not with a gauge, but with a deadweight tester. So this is with data taken in 1946, plotted as a delta P versus a delta T. This is a 24-hour flow, and this is the infinite conductivity vertical fracture solution, and you can see all the data exactly overlays, including this data towards the end. And this period here is when the engineer went home, you had to go to sleep. You know, nowadays you have these tools that you can record the data continuously. That would have been nice, but you could see that this data here also fell in line with there. And this solution wasn't invented until about 1972 or 1975. So good data taken in 46 fits a current analytic solution. With that PDTD, we did superposition analysis on all that data, and this is all these wells. We did a superposition analysis on all our data using that PDTD, and this is the fit. You know, this is the calculated, and this is observed. And the last flow rate was a reduction in flow rate. So this looks like a buildup, but it isn't. You know, because you cut the flow rate back, you had an increase in pressure. You know, so all these transients have been accounted for in a solution. And here we get a skin about a minus 5.3. Something to keep in mind here, you know, if you've ever been involved in non-Darcy flow behavior, for gas wells, we started out with the assumption there was no non-Darcy flow. And we didn't use any non-Darcy flow on any of these wells or any of these layers. It turns out when I show you the back pressure deliverability plots, they have slopes as low as 0.799. You know, everybody assumes that implies non-Darcy flow. That's another type of response that you're going to get from layered no crossflow reservoir behavior that was unexpected out of the study. To put you at ease with regard to, you know, because when we started, you'd give some of our results either as papers or you had testimony up there in Kansas. Everybody just assumed, we had assumed the permeabilities were basically uniform throughout. We used with the Ks for each layer at the individual well, and this is the permeability distribution for the Harrington or the low permeability layer. You know, this is a scale from 0 to 1, so we do have a variation in permeability that we interpolated from the values that we had at each individual well location using combination. I think I mentioned to you earlier, we took the phi K plot for the Harrington. We did our distribution of K in the Harrington and the difference between the total test, the KH, and that KH was assigned to the Kreider. And again, remember that we made no changes in our initial K distribution on any well from our original distribution, but the sum of the KHs of all layers had to be equal to that we got for the total well. And this is the distribution that we got for the Kreider. Okay, one interesting thing, and notice this apparent anomalous high. Well, this was the area that we were able to figure out later through the sum of the absolute open flows over the gas in place of the layer that we had too much K in a Kreider, and we needed more deliverability from the wind field to get the layer pressures to be about equal. So actually, two of the wells here, we figured that we'd frack down into the wind field when we were doing the stimulation of the Kreider. And when we did that, everything kind of fell into place. So even though it wasn't actually physically perforated there, once we did that, everything lined out. And we got in that direction again because we knew the layer pressures had to be equal between, very close to being equal between the crider and the wind field. And we got in that direction again because we knew the layer pressures had to be equal between, very close to being equal between the crider and the wind field. And this is the distribution in the wind field. Only 3 of the original wells were completed in the wind field, but we had to add those 2, basically 2 out in that area in order to get a proper match on everything, deliverability, the pressure cum, and layer pressure. I'm not going to dwell on this one other than to show you that I don't even know if this is in the paper on the work that we did, but this is a detailed description of the distribution of thicknesses and permeabilities and water saturations and porosities for each of the layers that we input into the model at the specific well location. So we didn't assume everything to be constant. And this is a key well match. This is one well, this is the buff where we drill the expendable well. And like I say up there, this is where we got 5 wells in the wind field where we figured out that's where they had to go to get the match. Now what we have here is PO-RZ versus cumulative production, and remember this is total cumulative production from the well, which it comes from all layers, whichever layers are contributing. The red dots, the reason you can tell the red dots are field data. Okay, we're 72-hour annual test that consists of a 72-hour shut-in pressure and a 72-hour drawdown. After you shut it in, you flow it for 72 hours. You measure the rate and flowing pressure. You also got the shut-in pressure before you turned it in. So that's where the red dots are squares, and people who are colorblind can't see them. But the blue circles is we physically shut the model in every June, which was approximately the period that the wells were tested annually. We shut it in to get a 72-hour shut-in pressure. We got that pressure out of the model, and then we floated for 72 hours, and we got that flowing pressure and rate, and that's the blue. You virtually exactly overlay, and you even see the inflection. These changes in slopes of the total system is indicating drainage that's occurring between wells within the study area. Otherwise, it would have been a perfect straight line. I'll show you later. We took a case that, well, let's close the section lines on all this, and let's see how dramatic drainage is after we got a match. And I'll show you what happens. And one thing that sticks out like a sore thumb, only when you close all the section lines does the total system volumetric average pressure is a perfect straight line. So this is the volumetric average pressure. The solid line is the volumetric average pressure of the crider within the 640-acre section. Okay. This is the wind field. This is the Harrington, and this is the total section itself. You can see from here, it's amazing that the 72-hour shut-in pressures exactly overlay the volumetric average pressure of the crider. Exactly, not approximately, but almost exactly. So the pressure that you're seeing when you shut these wells in is the pressure of the crider, period. You don't see this or this. Well, you're not going to see that. You don't see that or that. But if the crider, or if the other layers weren't there, you would have a different pressure response for a given cumulative production. So it does reflect it indirectly. You have to keep that in mind. People were arguing, well, the pressure doesn't mean anything. If I produce this total volume of gas only out of the crider, I would have a totally different pressure cum plot. Okay? It's really important to understand that it does reflect the production that came from the other layers, even though the pressure itself is not a pressure of that layer. It's a pressure that exists at this particular cum as a result of its production and the other production all simultaneously. Because a lot of people got caught in that logic that it means nothing. I can't get that match unless I've got it described perfectly with regard to the layer volume, each layer volume, its KHs, and its skins, or I can't get that match. Right, that match is basically pressure Qm. Now this is a match of the well deliverability. I plot as a back pressure curve. The observed shut-in pressure squared minus flowing. The equation is normally built for P-bar, but I don't have a P-bar. I just have a number. It's a 72-hour shut-in pressure. And the flowing pressure and the rate, and this is a plot with the field data or the red squares. The model simulation of the shutting in and the flowing is the blue circles. Pretty good, isn't it? And the slope, even though there's no non-Darcy flow at all, and any layer in the model, any layer, it's got an N value of 0.886. That was a surprise. And if I hadn't have started out and said, well, let's keep this simple, don't use non-Darcy flow in trying to do your superposition of all the KH and skin, otherwise you've got different numbers. And you would assume that there was non-Darcy flow in the problem. The replacement well that we drilled, the Strat, well, that's it's P over Z versus Qm. This is the same type of nomenclature, but we've only got 2 layers here. The other one we had 3. This is the Harrington. This is the Kreider. The well before the replacement well, you put on pump. The only reason it was coming down here because it was being drained. It was watering off. It wasn't producing its share. The offset wells were then at that time. Once we put it on pump, started producing it, we come back on, and we did nothing after when we drilled this well. We did nothing to change the description. We just put the same skin on the replacement well as the original well, and we adjusted nothing, and we got a perfect match. This is a key well for lots of reasons. One of them being, look at the layer pressure matches out of the model. This is not at the well bore. This is 2,000 feet away from the producing well. With the DST or the layer pressures in the Harrington was 314. In the model, it was 318. In the Kreider, it was 121. In the model, 128. In the Winfield, 141 and 137. The ability to match those layer pressures locks in everything. It becomes a unique solution. You can't get any other match of those layer pressures except with the way we had it described. Now, you could throw away volume, and I'll show you that later. You can throw away volume and get a real good match of pressure Qm and deliverability, but the layer pressures are equal. You had to throw away 20% of the pore volume to get that match. I'll show that later. And that's exactly the volume that they were coming up with in Kansas and said, this is our target gas. These are the pods that are out there because the historical match, the gas in place doesn't match the volumetric, so therefore these have to be isolated pods. That's the logic that was used. And that logic is used in a lot of areas for people to justify infill drilling at the Railroad Commission or Oklahoma Corporation Commission by trying to demonstrate P over Z versus Qm doesn't match your volumetric, so therefore there is a case for infill drilling. It works. They get it.
Mike, just a question. On your slide there with that buff number 1, well, the back pressure plot, the transient curves that were obtained right at its initial completion, do they have a slope of 1?
No. See, one of the problems, in fact, this one of the ones that we did the analysis on has a slope of about 0.788 something. And the reason it does is flow after flow. Okay? You have the transient, it's increasing sequence, so each of the transients of the previous flow adds another delta P onto each subsequent flow, so it pulls the points over to the left. We didn't have isochronal tests, so you couldn't get there from here. Okay? But the fact we matched all the superposition exactly, we would exactly reproduce the slope of the multipoint test, the flow after flow, when you plot it. I've got it here somewhere, but I didn't want to confuse the issue.
I'm just curious if you were working with it today on a new
we tried to run that in the model, and we answer this question, and it turns out some of the effect, I think, was due primarily to drainage effects of offset wells, smooth and monotonic.
Would you expect this when we go back to an N of 1
No.
on down the line?
No. One of the problems that exists, of course, about running any multi-point test now is that I'm just getting a pressure, and I know it doesn't represent P-bar. The original logic is all based on the assumption that it's an average reservoir pressure for a single layered system. And as we can see, the pressure we're getting represents nothing but the Kreider layer, a volumetric average. But the flow rates that we're getting are the flows of all of the layers together. And there would be a point where if you'd run over a whole sequence that there, well, just like we found in the model, when they curtailed us, we had backflow occurring in a wellbore. You could probably run an isochronal over a range of sequence until you got to the point where the pressures, the flow would start reversing, and then you see a displacement in the curve. Okay? That's exactly what we had when they ran multi-point tests on the Cook Inlet wells, where the pressures were different. It's an interesting idea, but how are you going to get people to spend the money to get the data? Maybe if it's worthwhile, you can possibly propose it. But what we ended up with with the Cook Inlet was they were running. You start off at the lower flow rates, and you have well, I can't remember exactly what the pressures were, but what ends up happening if you'd run a test, delta P squared versus Q, is at the beginning you're going to be flowing at a low flow rate, and you're going to be a part of the rate's going to be going into the other layer, okay? And you're going to be getting some at the surface. And then when you finally get at a high enough flow rate to where the bottom hole flowing pressure is lower than the shut-in pressure of the other layer, and the data exists because I analyzed the data for E and P. There was a shift in the deliverability curve to the right once the other layer started actually contributing. Up until then it was backflowing, so you actually had a negative. You could add an additional Q to this because a part was flowing backwards into the other layer. I finally got the flowing pressure below the shut-in pressure, then you had a big shift, and I had Qs from both layers now, and there wasn't any negative flow, any backflow. So this is a real possibility, but you'd have to take the effort, to run that type data, run a test to get that type data. That's a good question. There's a match of the strat well, the replacement well that was drilled, and again, I think the reason this was replacement is we drilled a deep test. It was dry, so we came up and completed it. This performance data was due to the well being wet, and that's why we tried it in the first place. You can see the data kind of shifting to the left, and it was all the way over here. We drilled a new well, installed a pumping jack to dewater it, and there's the deliverability tests on those wells. They exactly overlay the original well. It really didn't shift at all. Deliverability didn't shift. Those are one well at a time. There's the simultaneous match of all the pressure cumes in each well at each location. I mentioned to you earlier that we had to add a couple wells down here, but look at the match of the 72, the physical 72-hour shut-in and the physical 72-hour, the build-up of the model, as compared to the actual physical 72-hour shut-ins in drawdowns in the well in the field with backflow and everything else, and everything occurring simultaneously. And you can see it's an absolutely perfect match. All wells simultaneously on pressure versus Q. There's the match of deliverabilities on each of the wells simultaneously. Absolutely fantastic. And then also you have to realize that we match the layer pressures also on the buff within just a few pounds in each layer. So it was unique. It's a unique match. You can see here that the slope on this one here, even though there's no non-Darcy flow in any layer, has got an N value 0.799, which is normally interpreted to be reasonably severe turbulent flow in a reservoir, and it's not. You have to remember again what you're plotting is a shut-in pressure that only represents that one layer plus the rates from all layers, and you really have a bastard plot. But isn't it amazing how all the data comes down almost a perfect straight line, though? It's not moving all over the place or shifting. One thing we found, you got to be very careful because of the concept of superposition, is before we shut the well in for 72 hours in the model and also for the 72-hour drawdown, you had to make sure that we were producing at the rate that was produced in the field. The producing rate prior to shut-in affects what's going to happen for your 72-hour shut-in and 72-hour drawdown. So we had at least make sure the month prior to that we were using actual physical producing rates. It's a subtle point, but we got, we thought we were going to hearing, we had to try and keep everything so we can answer any question. Now here's a no crossflow case. We have everything matched now, and all we did was we put more than that. The other one was no crossflow too. Is what we did was seal the boundaries at every section line. Everything was matched, and now we sealed the boundaries at the section line, and you can see we totally destroyed everything. Here's the real data. Here's the model data. I don't think there's a single instant where this one looked preserved. That's almost preserved. Look how straight the total system volumetric average pressure is now. So you can see that you're able to see the drainage in the P over Z once you went backwards and realized that, hey, that should have been a straight line. It was a true volumetric system, and the drainage radius wasn't continuously changing, and that's why you can't do a one-well study, because there's no way you're going to proportion a proper R sub B in 3 layers because you have no idea what the rates are, not only in the well that you're looking at, but the offset wells too. And so you can't do a one-well study. Even though you do that, though, deliverability looks good. Even though we closed the section line. Well, we got the KH as described. Nothing's going to screw that up. Okay? Once you got the KH and skin described, it really don't make any difference what your pressure level is. Theoretically, things just going to go up and down the curve anyway. So you could kind of be deceived by thinking this is an excellent match. The problem is it's not a point-to-point match. Because once you got the KH and skin described, it's always going to trace this curve up and down. It can only go up and down. It's not going to move to the left and right, regardless how wrong your shut-in pressure is. If you take and we kept kind of screwing it down, and I don't remember why we only have this value, but when you put a crossflow factor as low as 0.005, you might call that 0. Remember, we're producing about 45 years. Now all of a sudden all layer pressures are over top each other. That's equivalent to complete crossflow. That same problem, like I said before, no matter how everything's screwed up, deliverability always looks good. So be careful that that you think that that's because you got a good deliverability match, the other isn't so bad that is 50%. Again, once you have it properly described, you're always going to go up and down that curve. Okay. Now this is the interesting one. With crossflow and throw away 20% of the volume. Very good POZ match, isn't it? Does everybody agree? Does somebody agree? Right? It looks fantastic, really. That's what they did up in Kansas. They only matched POZ, they didn't match deliverability. Because you're going to forecast in the future, you better have the right to deliverability. This is the same one. The same case, but now we've thrown away 20% of the volume. If you look at this P over Z, and that delivery, you say, boy, that's a perfect match. Which one's right? Well, if you go back to this one, and well, what's wrong with it? Well, the layer pressures are all equal. And we measured 320 pounds in one, 120, 140 in the other one. That's what's wrong. You had to throw away 20% of the volume, and you got a perfect match. But what would normally be considered a perfect match. Without the layer pressures, you're not going to get the right answer. And again, it was a 20% volume discrepancy that they were using as the justification for the target gas to do infill drilling in Kansas. But this starts getting in the area of non-uniqueness. Somebody says, well, it's non-unique. I want a model that isn't unique. I can match with a lot of different things. Once you get the layer pressures, there's only one answer that you can get. It is unique then. You eliminate the non-uniqueness of the problem. I sort of mentioned this to you earlier. A bilayer, this is the Qmax over G sub I of each layer of the Harrington, Kreider, and the Winfield. And the Qmax is the sum of the pseudo-steady state curves of every completion in that layer. Okay? So I have a Qmax over G sub I. This is the gas in place in each layer. This is the total. That very simple equation, you remember the one that we showed earlier? With a flowing pressure of 0 and all that other stuff, and Z equal 1. I would calculate to an economic rate of 10 MCF per day per well times 12 wells, 120. The Harrington layer should reach that 77 years, 25 years in the Kreider, and 26 in the Winfield, and a combing would be 90. Okay? That's simply, this is what we got running with a 3D model. We also ran it with a line pressure other than 0, and it's still the same answer. I think it's in the paper. The difference between 77 and 78 and 25, there is no difference. So you can handle a real complex problem with the simple equations. And again, this 91 years, this long producing, the time is basically a layering effect. So if you go back and you see some oil fields that have been producing since 1919 and they're still on production, you know what's the cause of it. It's layered no crossflow. The same thing with gas fields that have been producing a long time. This is a fundamental characteristic of a layered no crossflow reservoir. It's going to have a long life. And there's nothing you can do about it again. You do infill drilling, you accelerate. Okay, rate of take, that's the, if they decided to take a lot faster out of it, they might have reduced it. Well, it's the other way around. I think this is basically wide open, and this would be the way that they were actually producing it. Okay. We'll get into that a little later. Later, I think I've got some of those numbers or tables or charts. I mentioned earlier about how you can take this equation and, you know, the Qmax over G sub I. I tried to show you the difference between a model run and equations in order to get some times, and this again is just using this basic equation. If I want to make the Harrington in a Kreider deplete at the same pressure at the same time, I know that the ratio of these has to be equal. So I determine what it is for the Kreider, and I try and determine how many wells in do I have to drill in order to make these two equal. And you go down through the calculations, it turns out you'd have to drill your 29 wells or have a 20-acre spacing for the other two layers to equally deplete. To give you an idea, you have the pressure distribution at the end of the history match. This is the Harrington pressure in 1987. You can see the locations of the wells and the gradients within the low perm layer. You know, this is the well of the bottom, but this is where the expendable well was drilled. That's where we got the pressure. That's where we measured the pressure. So this is another factor you have to sort of keep in mind, is you just can't trade off in Qmax the K, the skin, and say the pressure. Because here we were out at a distance, there's a gradient. The permeability is going to determine what kind of gradient is going to occur out at that distance. So you have to be a little careful. But that only starts to become real significant when you get into, you know, looking at a tenth of a millidarcy permeability. Just wanted to show you that everything wasn't going down equally either, that there are gradients in the problem. With a Kreider pressure, at the same time, you can see it's relatively flat compared to the other Harrington, because you're looking at maybe 10 millidarcies here on average, and you can see the location of each of the individual wells. It's real flat in through here. In Winfield, this is one where we had only the 3 wells in it, but again, it gives you an idea what the pressure gradients were, and you can spot very quickly where the wells were. This particular, we didn't produce one of these outputs when we got to the 5 layer. There were the 5 wells in there. This is a summary of the results that we got out of a model study. The gas in place in Harrington, 15 billion, the Kreider 25, the Winfield 10, a total about 50. In 1989, about 40% recovery factor in Harrington and 78 in the Kreider and about 69 in Winfield. The cumulative production to the year 2056 would be about 10.7 or 71%. 95%, 93 for a total overall of 88%. But no infill well was drilled in this particular case, and it lasted for 67 years. Okay. All right. Now this is a case where we ran it with an infill well. We cut the time in half to abandonment, but you see the recovery hadn't changed, and basically the layer pressures haven't changed in the model. By drilling the infill well, we didn't get, you don't lower, what we ended up doing was swapping these two around a little bit, but in essence there's no lowering of the abandonment pressure due to infill drilling. This shows it in a little different form. I think these are conclusions in the paper. This probably won't show up good on the camera, but it's about the same thing that we showed before. The current operations, in other words, we're producing at a constant rate against a 20-pound line pressure, no infill well, with an infill well, layer pressure 144 pound, 23, 25, 142, 25, 27. And fraction recovery, this would last from the very beginning, 1946, and this is the abandonment rate of 10 MCF per day. From 1946, when the field actually came on production, the total life of the field is going to be 108 years. The time of abandonment from 1989 will be 65 years, and we'll cut it in half to 33. With an infill well, we would shorten it to 76 years, a total life, or actually 33 years from 1989. But again, there's no change in abandonment pressure. Now, even if we had produced, remember it was 108 years for the life of the field, even if we had produced the field wide open from the beginning, without an infill well, we just produced it wide open from the beginning, it would have taken 82 years to reach an abandonment rate of 10 MCF per day per well. And the abandonment pressure would have been higher. Instead of 144, it would have been 153. There is a certain degree of rate sensitivity. The lower the rate, the lower that you're able to achieve the abandonment pressure. So this is with the 82 years is still a long time. Even if you'd produced wide open from the very beginning, it's the best that you could do. I mentioned earlier I didn't have this out as a copy. My overheads. This is in a paper where we're trying to demonstrate for the 12-section study area, using the pseudo-steady-state equation with a zero flowing pressure, you get 75 years, 27, 21, or a total of 86. The 3D model with the back pressure of 20 pounds. The time to abandonment is going to be 76, 25, 20, and 82. The current operations with you produce a constant rate go on decline be 180. The basic point I was trying to get to earlier was that you can do these calculations on the back of an envelope using this equation here. This is all that was used. You have to generate these numbers with all the simplifying assumptions, even with a zero flowing pressure, and the model was run with a 20. These answers are essentially the same. For engineering purposes, to decide what to do, they're essentially the same. All right, we got the model matched. And if we had produced it wide open from the beginning, if we took the 12-section model that was history matched and produced it wide open from the beginning, this would be the rate time plot for the 12-section model, and that would give a B of 0.6. If you go to the table, well, let me go on. The volume ratio at the beginning, you had twice as much in the more permeable layer as the less permeable layer, okay? You had 2.3 to 1. We're going on decline now, and we've had the differential depletion. You've seen the 300 pounds and the 100 pounds. Now, in terms of gas in place, the volume ratio ready to go on decline now is switched to 1 to 2. With a Qmax over G sub I from the model here is 10. Over here it's 50. If you go to the table, now also recognize that the B value here is 1. Over here it's 0.6. If you go to the table, in case I have to refer to it, the Qmax over G sub I of 50, the volume ratio 2 to 1, so I'll come here to 2 to 1. The 50 in here, I should expect a B value somewhere around 0.6, and we get a B value of 0.6. For this one here, the Qmax over G sub I is 10. The volume ratio now is switched to 1 over 2. I come to 1 over 2, and 10, the expected B value should be 1. This gets back that you're dealing with the original gas in place, and I think I showed you earlier. We went down into the Texas Hugoton, and sure enough, the wells are on decline back in 72, plotted the rate time. And we got a B value of 1, just exactly what we were getting out of the model, taking the model and going into decline. So that, we're able to take what we got out of that and extrapolate it all the way into Texas Hugoton.